Good morning, students. Let us start the AEC class. We were discussing about this DBM in the previous class. And I was telling you an example of the cell phone. Not only the cell phone or Bluetooth device or Zigbee device or to some extent even all the portable wireless devices. They all draw power actually in milliwatts, and it is necessary that we measure power in terms of milliwatts as far as RF transmission is concerned. I was telling you earlier that as far as the audio equipments are concerned, we can measure power in watts, or even if electrical appliances are concerned, we can measure power in watts. But when it is compared to the RF transmission, RF power is a very expensive power. In the sense, if you are using a 3G cell phone, 2.4 gigahertz of radio carrier generating 2.4 gigahertz and transmitting 2.4 gigahertz is an expensive affair there, where we have to overcome the effects of interference, noise, and we should still maintain the signal integrity for the effective communication. So in many such cases where RF power is utilized, power is very expensive and power need not be in watts there. There are regulations, international regulations as far as the RF's maximum power transmission is concerned. Because if RF crosses a certain limit, it can be harmful to the human body as well. For example, a mobile phone can transmit maximum of 2 watts of RF power. I am talking about 2 watts of RF power. Whereas your regular electric bulb can be 60 watts to 100 watts and your electric fan can be 1000 watts, but your mobile phone in the RF domain is going to transmit maximum 2 watts of power. If it is more than that, then it will become harmful to the living bodies as well. So that way there are many such regulations. You can go through them in your free time. You can search for a term called BBB and SAR. BBB stands for a brain-blood barrier and SAR stands for specific absorption rate. These are the terms that are utilized in relationship with the human body itself, and it is dangerous for the human body to get exposed to the radiation in larger amount of power. That is why we will be using a term called dBm, decibel in terms of milliwatts, and we will be measuring all the power emissions of the RF devices using dBm itself. So let me proceed now. You can see this particular tabular column. 1 watt corresponds to plus 30 dBm. You can see the formula here. P in dBm equals 10 log of P by 1 milliwatt. So at the top it is 1 watt, at the bottom it is 1 milliwatt. This milliwatt goes up, it becomes 10 power 3. So log of 10 power 3 is 3. 3 into 10 is 30 dBm. So 1 watt corresponds to plus 30 dBm. 100 milliwatt, that is 0.1 watt, corresponds to plus 20 dBm accordingly, in accordance with this particular formula. 10 milliwatt corresponds to 10 dBm and 1 milliwatt corresponds to 0 dBm. If the numerator is 1 milliwatt, denominator is 1 milliwatt, log of 1 is 0, so we get 0 dBm. Now it doesn't mean that power is 0. It is 0 dBm, means input power and output power both are 1 milliwatt. In that case, we call it as 0 dBm. Please remember that. Now, if the power is still lesser, let us say it is 0.1 milliwatt or 100 microwatt, and then it is minus 10 dBm. If it's 10 microwatt, minus 20 dBm. If it is 1 microwatt, minus 30 dBm. Why? On the top you have 1 microwatt, at the bottom you have 1 milliwatt. So, numerator will be having 10 power minus 6 by 10 power minus 3 is actually 10 power minus 3. So it is minus 3 into 10 is minus 30 dBm. Now to give you a real life example, the mobile phone will have a received power of up to minus 90 dBm. I am talking about received power, not about transmitted power. Minus 90 to minus 110 dBm is normally the range where the mobile phones receive power. If at all the mobile phone is receiving a power which is less than minus 110 dBm, then you will get a message as network coverage problem or not reachable message you will get. But still, if you send an SMS at that time, SMS will go. Voice call will not go, but SMS will go, because SMS is using a different type of RF channel called control channel, which is different from the voice channel. So in the control channel, the power can go on up to minus 120 dBm also. That means the cell phone will be sensitive till minus 120 dBm. If at all the cell phone is not receiving a power which is not even minus 120 dBm, if it is less than that, then the message also will not go and the voice call also will not go. So remember this, cell phone has a maximum received power of minus 90 dBm and a minimum received power of around minus 110 dBm. That is how they define the threshold. Now you can see the cell phone is not receiving power even in microwatts. It is going to receive power in nanowatts and in picowatts, but its transmitted power can be up to maximum 2 watts, but its received power can be in nanowatts and picowatts. That is why we use this unit called dBm, decibel in terms of milliwatts. Now similarly, there is something called VDBV. Just like we have PDBM, we have VDBV. That voltage in decibel V is nothing but 20 log of V, or V equals antilog of VDBV divided by 20. So if it is 1 volt, 1 volt by 1 volt is 0 dBV. If it is 100 millivolt or 0.1 volt, 0.1 volt by 1 volt is naturally, that is 10 power 0.1 volt. So that will become 10 power minus 1 into 20, because in voltage it is multiplied by 20. So minus 1 into 20 will be minus 20 dBV. 10 millivolt corresponds to minus 40 dBV. 1 millivolt corresponds to minus 60 dBV. This way it goes on. 100 microvolts corresponds to minus 80 dBV. 10 microvolts corresponds to minus 100 dBV. 1 microvolts corresponds to minus 120 dBV. You can relate this with this formula. 1 microvolt is 10 power minus 6. 10 power minus 6 into 20 is the 6 into 20 is 120 minus 120 dBV. This way we can measure the voltages in the RF domain. Okay, so we can measure power in terms of dBm and we can measure voltage in terms of dBV. These are the units which we use when we have measurements for RF applications. Let us solve an exercise. Here as a funny way or a humorous way, I am showing the exercise done by adults, either in the gymnasium or this fellow is trying to touch his own feet, which is very difficult for him. So the funny thing apart, I add some pictures only for you to have some paradigm shift. My belief is always that learning should be fun, whereas examination should be serious. While learning, you should learn it, or I should teach it in a harmonious manner where we both should enjoy the process of teaching learning. Whereas examination has to be very serious, because examination is part of your evaluation. That is why I put some funny pictures here. Now let us try to solve one exercise. An amplifier rated at 50 watt output is connected to an 8 ohms speaker. Its power gain is 30 dB and voltage gain is 42 dB. Find the input power, input voltage and impedance required for the rated output. So in the problem it is given is the rated output is 50 watts and the speaker connected that the output is 8 ohms. So output impedance is given and output power is given, and the power gain of the system is given, voltage gain of the system is given. We also know that the power gain is 10 log of P0 by Pi, voltage gain is 20 log of V0 by Vi. We can use those formulae here now. Now he is asking us to find the input power and the input voltage for this particular amplifier along with the impedance that is required for the rated output. That means we should match the impedance for maximum power transfer. So let us try to solve this exercise. Let us start from the output side only because the data at the output is given now. So Pi is now 50 by antilog of 3. Why? Here it is given power gain is 30 dB. When power gain is 30 dB, 30 equals 10 log of P naught by Pi. So using the same formula in the other way, we can write Pi equals 50 watt output. P naught is 50 watt divided by antilog of 3 because the power gain given is 30 dB, that 30 by 10 is 3. So we are using this formula. Using the formula we get Pi equals 50 milliwatt. Now we can go back and check again. 50 watt output, 50 milliwatt input. 10 log of 50 by 50 milli is what? 10 log of 10 power 3 there. Minus 3 goes to the numerator, becomes plus 3. So 3 into 10 is 30 dB. You will get the same answer. So we are using the same formula in a different way. We get input power as 50 milliwatt. Okay. Now V naught is square root of 50 into 8. We also know that P is V square by R. Right. So V is square root of P by R. P is 50 watt. R is 8 ohms at the output. So output voltage is 20 volts. Now when we get this output voltage gain is given. So we can find out input voltage also. We have found out the input power now. We can find out the input voltage also using the same formula. What is that? Voltage gain in dB is equal to 20 log of V naught by Vi. Now we know V naught. We can find out Vi by using the antilog concept. So Vi is 20 divided by antilog of 2.1. Why this 2.1? Because of this 42 dB. So output voltage 20 volts divided by antilog of 2.1 because it is now 42 divided by 20. 42 divided by 20 is 2.1. So we get the input voltage as 159 millivolts. You can again observe this. 50 milliwatts is the input power, 50 watts is the output power. Whereas 159 milliwatts is the input power, 159 millivolts is the input voltage and 20 volts is the output voltage. You can see the difference here. Power gain is 30 dB, voltage gain is 42 dB because we have impedances there. Now we have to find out the input impedance. That is the last part here. How to find the input impedance now? Ri is square root of 159 millivolts divided by 50 milliwatt. We also know that P equals V square by R, or R is equal to V square by P, right? So Vi squared, input impedance is Vi squared, 159 millivolt squared divided by wattage P, 50 milliwatt at the input. So we get Ri as 0.51 ohms. Okay. This way input impedance is 0.51 ohms, input voltage is 159 millivolt, and that is how the input power becomes 50 milliwatt. Now because the amplifier is having 30 dB gain and 30 dB power gain and 40 dB voltage gain, we get the respective output. So there is no impedance matching as such because all the data are already given. It is not required to do an impedance matching. We have to only find out the unknown quantities or unknown values. Let me proceed further. Let us see something called as Bode plots. One scientist called Bode has contributed remarkably for the purpose of gain and bandwidth measurements, and that plot is called as a Bode plot. Let us see that. There are some general terms here. In general, in music, octave refers to double the frequency. In general, in music we have bass and voice and treble. Sometimes they call it as bass and medium and treble. The frequency which is below 300 hertz is generally called as bass. Sometimes they call bass also, sometimes they call bass also. you have a guitar called bass guitar. Actually, it is BASS. Bass guitar means the guitar produces sound which is less than 300 hertz. 300 to 3400 hertz is called as human voice frequency range. Above 3400 hertz is called as treble. So, right from 20 hertz till 20 kilohertz, we have an audio frequency range, out of which the voice frequency range is from 300 to 3400 hertz, above which it is a higher frequency range. In general, flute or veena or high frequency guitars, the normal guitar, they all produce sound which is more than 3400 hertz, whereas tabla, drums, mridangam, ghatam, or the bass guitar or bass guitar, they produce a sound which is less than 300 hertz. In fact, in a guitar or in a veena, if the string is thicker, then the frequency will be lesser. If the string is thinner, then the frequency will be more. Why? The reason is, if the string is thicker, its number of vibrations per second will be lesser. So, its frequency output will be lesser only. If the string is thinner, its number of vibrations per second will be more. So, naturally the frequency will be more. So, music is basically one vocalist who is a singer, and then one type of instruments which is related to bass or bass, and other type of instruments related to treble. So, in any song, you will find all these three components. One is a singer who is singing, also called as vocalist, and then you will have mridangam or ghatam or tabla. Such instruments are called percussion instruments. They produce frequency right from 20 till 300. Sometimes it can slightly go beyond 300 also. Similarly, there will be other instruments like a flute or keyboard or veena or sitar or guitar. They produce sounds which are having frequencies larger than 3400 hertz. So now, why I am telling all these things is, this particular term called octave refers to music, where they say whenever there is double the frequency, they refer to as octave. Here, octa does not mean 8. Don't get confused that way. Octave does not mean 8. In the terms of music, octave means double the frequency. Okay, and decade refers to 10 times the frequency. Decade is accurate. Deca means 10 only. So, if any frequency is 10 times the other one, then we call it as one decade. And if any frequency is double the other one, then we call it as one octave. These are the terminologies used. Now, why should we refer to the terms which are utilized in music? Because we are going to design amplifiers for music as well. When we design audio amplifiers, that is meant to amplify the music itself. When a vocalist is singing in front of the mic set, and a guitarist and a tabla player, when they are playing their instruments in front of the mic set only, right? And all these three mic sets will be connected, not just three, there can be many mic sets depending upon the performers. All these mic sets will be connected to a stereo system, or it is connected to an audio amplifier system, and the audio amplifier will combine all these signals together, and there is something called equalizer also in the audio amplifier. You can set an individual gain for each set of frequencies. For bass or bass, there can be a different set of power gain, and for vocalist or for a singer, there can be a different set of power gain for the voice, and even for the treble high frequency range, there can be a different set of power gain. And that is where you will have so many lights glowing up and down. Those lights are indicating the gain that is changing with respect to the equalizer. Many times you can set this equalizer manually also. In your computer system, you can actually set this equalizer gain on your own for any playing of the music. So when they are all important for us, we are going to design audio amplifiers, and we are also going to design equalizers as well with variable gains. That is why the terminologies which are used in music are important for us as well. We work as audio engineers and radio engineers. When we plot the graph of frequency versus gain, the linear scale is not suitable. Why? Right from 0 Hertz, if at all we go till 1 gigahertz, now think about the linear scale. Can we have x-axis right from 0 till 1 followed by 9 zeros? How big should the paper be, or how big should the x-axis be? That is the problem which we have. So we cannot use a linear scale. We require x-axis to contain octaves as well as decades. So what we do is, we go for a different type of plot now. That plot itself is Bode plot. Bode actually developed the method of having such plots. So here y-axis can be linear. In y-axis we can plot a gain again in decibels. We will have 10 dB, 20 dB, 30 dB, 40 dB. That way we can use y-axis. That is why we have decibels now, right? Otherwise, if you don't have decibels, how do you plot a gain of, let us say, 1 lakh times or 10 lakh times or 1 crore times? Y-axis also cannot be linear. But fortunately, we have this unit called decibel, where we use this decibel to plot gain at y-axis. But what about x-axis? In x-axis, we cannot use a linear scale when we go for a frequency up to 1 gigahertz. So the solution is, compress this linear scale into some other scale. That also again is a logarithmic scale. Just like y-axis is in decibels, that is also logarithm only. We plot this graph in such a way that we compress the x-axis into logarithmic scale. That is when we use octaves and decades here. When we use that logarithmic scale in x-axis, now we call this particular graph sheet as a semilog sheet. The reason is, x-axis is in logarithm, y-axis we use linear only, but in y-axis we plot the gain in decibels. So such graph we call it as semilog graph, and when we plot such response, that itself is Bode plot. So therefore, semilog graph sheet is used where x-axis is compressed. That's what I told you now. When we use the semi-log, semi means what? Half. Why do we call it as semi-log now? Because only x-axis is log, y-axis is linear. In y-axis we use gain in decibels. Even though decibels are log, we are not plotting that in the y-axis. We are using the decibel gain terms like 10 dB, 20 dB, 30 dB, 40 dB, and that way we go on. So y-axis remains linear, x-axis remains logarithmic. So we call it as half log graph sheet called semi-log graph sheet. Such plot is called Bode plot. You can see the picture here. The picture at the top, that A is a linear scale, but the B is not a linear scale. You can see it's a logarithmic scale. You can see octave also, you can see decade also here, right? Into 2 becomes it is octave, into 10 becomes it is decade. Now you can see here, from 0 to 10, all the dimensions are equally divided here. But below, from 0 to 10 or 1 to 10, not from 0 to 10, 1 to 10, they are not equally divided. They are compressed. And there is a ratio for this particular compression. It is not a trial and error method. It's a proven mathematical calculation. That is where Bode's contribution comes into picture. Now we can print the graph sheet as per the lower scale now. And we can go from 1 to 10, again 10 to 100, 100 to 1000, 1000 to 10,000, 10,000 to 1 lakh, 1 lakh to 10 lakhs, 10 lakhs to 1 crore. That way we can go on. This way we can compress the x-axis. You can see here, the x-axis is compressed here. You don't have to think that A and B are of same dimension. For the sake of illustration, the textbook authors have printed this picture in this manner. Otherwise, if at all this is 1 and 2 is there, if I bring this 1 and 2 in this dimension, then all the other things will be compressed actually. So that way x-axis remains compressed, and there is a specific ratio for this compression. It is not simply done as a trial and error, or simply not done approximately. Now this is that graph sheet. This is that semilog graph sheet, where you can see y-axis is the linear scale, 1, 2, 3, 4, 5, 6, it can go on. Whereas x-axis you can see 1, 2, then 3, then 4, 5, 6, 7, 8, 9, here 10. Again, it is written as 1 because We can name it as 10, or we can start with 10 also, we can name it as 100. It is up to us. If at all we want to plot the frequency response, we need not start from 1 Hertz here. We can start from 10 Hertz also, or we can start from 1000 Hertz also, we can start from 100 Hertz also. If at all we start from 100 Hertz, we can name this as 100 itself, we can write in the scale, and here we can write as 1000, here we can write as 10,000. It is up to us to make use of this graph sheet. But you can see here, the x-axis is being compressed till that 1 decade. Again, later on, the ratio is remained here. From this 1 decade to the next decade, you can see again there is a compression. This compression ratio is fixed. How is it fixed? You can see it. This is what Bode did. Log of 2 to the base 10 is 0.3010, so it is 30% approximately. He took the log of this itself. Now, log of 3 is what? Log of 3 is 0.4771. So, into 10 is around, into 100 is around 47.7%. That can be taken as 48%. So, here it is 30%, here it is 48%. That way, you can see the compression. That means, between 1 to 2, total of 30% of the length between this one and this one. Let us say this is 1, this is 10. In between them, we assume the total length. The total length 30% is between 1 to 2. The total length 48% is between 1 to 3. Same way, log of 4 is 0.6021. It is around 60%. So, the total length, if it is 100%, in between 1 and 4, it is 60%. Same way, you can see it goes on. Log of 5 is around 70%. Log of 6 is around 78%. Log of 7 is around 85%. Log of 8 is around 90%. And a log of 9 is around 95%. And anyhow, log of 10 here is 1. This is what Bode ingeniously developed. That means he thought of a graph sheet which can have this non-uniformity also, but that fixation also. So now the same ratio will be replicated other side. You can see the same ratio here. By taking the log of each division, he is fixing the gap between 1 and 2, 1 and 3, 1 and 4, that way it goes on. So now this graph sheet you can use for plotting the frequency response. In the y-axis we can plot the gain in decibels, and in the x-axis we can have right from 10 Hertz, 100 Hertz, 1000 Hertz, 10,000 Hertz, 1 lakh Hertz, that way it goes on. This graph sheet will be utilized by you when we start the offline lab classes, where you will have to measure the gain versus frequency, and you will have to plot the frequency response on your own. On the other hand, when you start working with the software called PSpice, that is also going to plot this graph in the semi-log sheet only. Okay. If at all you have any questions, you can put it in the chat box, or else I'll continue the class as such. Now you can see this D1 and D2, there is this fixation. We will not go into too much detail here, but still I want you to know the basics, that's why I have put all these things here. There is a detail of D1 and D2 there as per this log. So if it is 10 power x first, then it can be 10 power x plus 1. In between them, we can see the compression there. That is how it is now. Between 1 to 2, it is 30%, then it is 48%, then it is 60%, then it is 70%, then it is 78%, then it is 85%, then it is 90% and 95%. That way it goes on. It is the same ratio here. That is why he is indicating D1 separately, D2 separately. And he gives a brief explanation for this also. Now the value is 10 power x into 10 power d1 by d2. That way he can fix the ratio. So if the point marked is quarter inch away from 10 square line, and if the distance between 10 square and 10 cube lines is 3/4 inch, then the value is 10 square into 10 power 1/4 by 3/4, that is 10 power 7 by 3 equals to 15. That way we can actually compute the value for a given division. Actually, we will not go into such minute details. What he is trying to tell is, let us say you want to measure a point somewhere in between. There are these blue lines which are distinctly marked as 2, 3, 4, 5, 6, 7, 8, 9. And we actually know if this is now 10, we know this is 20, 30, 40 like that. Again, after 90, it is 100. After 100, we know this is 200, 300, 400, 500 like that. Now, the thing is, if at all we have to measure a value which is somewhere in between these lines, again the graph sheet is again divided into the subdivisions here. You can see the subdivisions here. Even the subdivisions will have the same ratio. Between 2 and 3, you can see the compression again. Between 1 and 2, you can see the compression again. That means, now this is corresponding to 100 means, this will be corresponding to, this will be corresponding to 200 means, now this will be 110, 120, 130, 140, 150, 160, 170, 180, 190 and 200. That way you will have the divisions. If at all you want to measure a point, you can easily measure that way. Now, why all these minute details are told is, if at all you will have a point in between them where you have no vertical line. Let us say in between them you have to measure a point, you have no vertical line. How do you actually get a value of that particular point? For example, wherever I am moving my mouse here now, if at all you have a point somewhere here in between this blue line and the black line. Now, what is the value to be taken there? If that is the point, then the D1 and D2 can be measured, and accordingly this formula can be utilized. So, up to this much of accuracy, Bode has given us the directions to plot his plot. We call it as Bode plot to honor him. Otherwise, sometimes we will also call it as simulograph. But in our experiments, we will not be going into these many minute details. What we do is we approximately measure it. What we do, let us say I have a point somewhere here. Now this is 100, this is 110, approximately we take it as 105. That's all. It does not matter as much because the x-axis is compressed. Okay. Let me proceed. You can see a practical Bode plot here, where we had seen earlier that at the lower frequency range we will have a reduction in gain, that is because of the external capacitances, and at a higher frequency we will have a reduction in gain, that is because of the internal capacitances. In between we will have a maximum gain, and I had already told you how do we measure F1 and F2. We corresponded to 0.707 of the maximum gain. The reason for that 0.707 and so I had told you, P equals Vi by 2, that is V by root 2 into I by root 2. We are going to plot the voltage gain here. So, V by root 2 corresponds to 1 over root 2 equals 0.707. That is how this particular point here corresponding to this F1 is 0.707 into the maximum voltage gain. Similarly, for F2 also it is 0.707 into maximum voltage gain. So, approximately we should say it is 71% of the maximum gain, where we mark these 2 points F1 and F2 and we measure the bandwidth as F2 minus F1. Why we do not measure exact at the midpoint? As I told you, it is a non-linear line, non-linear curve. So, it will be difficult to exactly mark 2 points there. That is why we always have this general notion in our life also that if there is an opinion which is crossing 50%, that only will be taken as the correct opinion for that moment. If there is a decision to be taken by a group of people, if more than 50% of the group are agreeing to one particular point, then that only will be considered as the final decision. Same way here, we take it as 50% of the maximum power, that is around 71% of the maximum voltage. That is this practical Bode plot. Now, before F1 and after F2, the dB gain decreases 20 dB per decade. Now, if at all we measure this particular reduction in the gain, it is following a certain ratio of reduction of 20 decibels per decade. Decade is multiple of 10. So, the gain will reduce here between 100 to 1000, that 100 to 1000 is 1 decade, or 10 to 100 is also 1 decade. There we can observe that the reduction in gain is around 20 dB. So, actually this reduction in gain depends on the circuitry itself. More about it you will be studying in the future courses, not in this particular course. You will study about first order filter, second order filter, third order filter, go on like that till nth order filter. More the order of the filter, more will be this particular reduction in gain. You will study about it later on when you study these courses in the 4th semester or in the 5th semester. Okay. So, this particular thing is called as roll off. This particular factor, it is actually nothing but rolling off. Imagine someone is or something is there here at the top. Gradually when it falls down, it is going to roll down. So, it is called roll off factor. So, now the roll off factor in this particular case is minus 20 dB per decade. So, before F1 and after F2, the dB gain decreases at 20 dB per decade. This occurs due to either coupling capacitor or bypass capacitor, whichever is dominant. What is the meaning of dominant? We will be seeing later on. Right now, you don't worry. Whichever is dominant, we have a bypass capacitor, we have a coupling capacitor, both we have. Now, one of them will be dominant in the circuitry. Based on that, we will have this decrease in the gain. Hence, the roll-off factor for this amplifier is 20 dB per decade. Because we have a single capacitor, here the roll-off factor is 20 dB per decade. If at all we have two capacitors there, then we call it as second stage. Now, in our amplifier, at the input, we have a single capacitor. And at the input, we have an input impedance. That means it is a single stage there. If there are two stages, then it will become 40 dB per decade. If there are three stages, it will become 60 dB per decade, because more and more of R and C means more and more of loss there. But as we have been dealing with only single stage amplifier till now, we only have a single coupling capacitor and then we have a single input impedance there. We can relate it as single stage at the input. So, we have 20 dB per decade, that is the roll-off factor. Now, as I told you, don't worry about this dominant condition. We will be working out those exercises in future. Now, the ideal Bode plot according to Bode is there is a roll-off factor of 20 dB per decade, then there is a linear gain in between, and then there is again a roll-off factor of 20 dB per decade later on. So, according to Bode, in between F1 and F2, the gain must be completely uniform. But it does not happen that way. Why? Because transistors are non-linear. Our circuit itself is non-linear. When our circuit's behavior is non-linear, we cannot have an ideal Bode plot. So, we are getting a practical Bode plot as shown here. Now, what is the difference between ideal Bode plot and practical Bode plot? Ideal Bode plot is completely mathematical. Mathematical in the sense, Bode says because of that circuit at the input, we will have a 20 dB per decade loss. Later on, we will have continuous voltage gain. Then again, due to the internal capacitances, we will have a loss or attenuation. So, this is a mathematically arrived plot, whereas our circuitry is non-linear. So, practically we get a non-linear Bode plot only. When you plot this curve in the lab experiment, you are going to get this way only. Then why do we discuss the ideal Bode plot? We discuss the ideal Bode plot only for the sake of mathematical analysis, because it is very difficult to apply mathematics here in the non-linear region. Wherever the curve is going down, there it is continuously changing. Later on, you can see that later on, after it is coming down, it is remaining a straight line here. And whereas somewhere in the region of transition, it is very difficult to arrive at the slope. So, Bode says, let us simply write a 20 dB per decade line, and let us simply write a horizontal line. Let us simply write one more 20 dB per decade line. Now, this is an ideal Bode plot, ignoring the small non-linear portion there. That is an ideal Bode plot. Ideal Bode plot helps us in analyzing mathematically in an easier way. Coming to the human's auditory response. Let us see how our ears respond to sound. That is also important. Why? We speak through mouth and then we listen through ears. Now the same thing, the same speech, we put it to an amplifier. Again, the amplifier's output also, we listen through our ears only. So between the singers and the audience, there is the audio system there. Now the singers are singing using their instruments and using their vocal cords, but the audience is listening through their ears. In between them, there is that amplifier system. So it is better that we understand our auditory response also, or the response of the ear. The human ear responds to changes in audio power levels in a common logarithmic fashion. That is the wonderful thing here. The human ear's response is also logarithmic in nature. Okay, I'm going to tell you more details now. The human ear responds to changes in audio power levels in a common logarithmic fashion. Common logarithm means log to the base 10, which means, let us say right now I'm speaking to you. Let us say right now my speech level is 2. Imagine that way. A level of 2. Imagine that way. Now I increase my speech, let us say to 10 times more, 20. Suddenly my voice level increases to 20 from 2. It is actually 10 times more. But you will feel as if it is only double. You will feel as if it is only 2 into 2 is 4. That is logarithmic fashion. Which means the amplitude may suddenly raise to 10 times, but the ear will not respond linearly. Why? The ear is made up of a cochlear bone and a cavity and a fluid, right? The ear will have a long cavity, then it will have a cochlear bone structure inside which there is a fluid. Now the fluid will move according to the sound waves which are coming into the ear canal. Then you will have a tympanic membrane. That membrane will vibrate and the membrane will transmit the electrical impulses into the cochlear nerves. And that is when these nerves are connected to the brain and electrical impulses go to the brain, and that is when you listen to a sound. Sound is acoustic, whereas inside your brain it is bioelectrical signal. The ear is going to convert the audio signal into a bioelectrical signal. So the response of the ear is logarithmic. Why? There is a fluid there, there is a membrane there, cochlear bones are there, a cavity is there. They all need not respond to the outside sound in a linear fashion. It is a complicated structure. So now, when the human ear is responding to changes in the audio power level, it is in a common logarithmic fashion. That means, if at all you should feel that if my speech is double its amplitude, then I should raise my voice to 10 times. That is how ear is responding. Now this is important. I will tell you why this is important later on now. Maybe in today's class or maybe in the next class, because already time is up now. I will not hurry up in these things. If at all I stop the class now, in the next class I will start this once again. Now look at this point. 0.2 nanobar pressure level corresponds to the threshold of hearing, which gets mentioned as 0 dBs. 0 dBs. It is not zero sound, 0 dB with respect to sound. That means if any sound has to exert a pressure of 0.2 nanobar on your tympanic membrane, any sound which goes into your eardrum, it should exert a pressure of 0.2 nanobar. That is called as threshold of hearing. If any sound which is less than this particular pressure, you will not be able to hear this at all. That is called threshold of hearing. We are talking about the human auditory response. Please remember, we are talking about the human auditory response. Cats can listen to sounds which are smaller than this. Dogs can listen to this sound which is smaller than this. In fact, all the nocturnal animals, the animals which remain awake at night time, they can listen to this sound which are smaller than this. Most of the hunting animals can listen to this sound which is smaller than this. Most of the animals who become a prey also, they also can listen to a sound which is smaller than this. A deer and a tiger both have an ear which can be much more sensitive than the human ear. Okay, that is why you can see the deer and the cattle, they can make their ears straight also. They can make their ears straight as if they are focusing to a sound, they are listening to that particular sound, they are picking up more amount of sound there by the vertical position of their ears. That is how God has made many varieties with many bodies. But coming back to the human's auditory response, human beings can listen to a sound which can have only 0.2 nanobar pressure. If the pressure is less than that, human beings will not be able to listen to that particular sound. That is called as threshold